Let's begin a new topic involving entropy, and we'll begin by solving a few problems where we're required to get entropy values from tables. Using the appropriate table, determine the indicated property. In each case, locate the state on sketches of TB and TS diagrams. And then we're giving 4 specific cases. Let's look at the first one. This will be water, which is a pressure at 0.4 bar. It has an enthalpy of 1477.14 kilojoules per kilogram. And we're asked to find the specific entropy in kilojoules per kilogram K. So as always, when we have an unknown phase, we'll start in the saturation table. So we'll go to the water saturation table at a pressure of 0.4 bar. And we'll note that the value of specific enthalpy that we're given, this 1477, is in between the values of H sub F and H sub G that we find in the table at 0.4 bar. And so this indicates that we have a saturated mixture. And when we have a saturated mixture, we start by calculating the quality. So the quality is just H minus H sub F over H sub G minus H sub F. And we have all those values here. Calculate a quality of 50%. So I'm going to plot that on a TV or a TS diagram. And the plot will always look the same for these two properties. So I'm just going to call the horizontal axis here the specific volume or the specific entropy. And the plot will look the same. So here we are. We have a saturated mixture with a quality of 50%. Sitting on the pressure of 0.4 bar. Now that we know the quality, we can calculate the entropy for this mixture. So from the same line in the table where we got H sub F and H sub G, we get S sub F and S sub G. So this finding these entropy values in the tables tells us that entropy is just another intrinsic property of this substance or any substance. So now we can go ahead and calculate the specific entropy. It's just S is S sub F plus the quality times S sub G minus S sub F. And when we plug in all of these table values, we calculate that the specific entropy at this state is 4.3480 kilojoules per kilogram K. Our second problem is water at a pressure of 10 bar, having an internal energy of 3124.4 kilojoules per kilogram. And we're asked to find the specific entropy. So we'll always begin in the saturated water table when we have an unknown phase. And we will look at pressure of 10 bar. And we'll note that the internal energy of a saturated vapor at 10 bar is 2583.6 kilojoules per kilogram. Well, U sub G is less than the value of U that we're given. So that informs us that we have a superheated vapor. So now I'm going to go to the water superheat table at 10 bar, and I'm going to look for an internal energy of 3124.4 kilojoules per kilogram. And I'm going to find it in the row that has a temperature of 500 degrees C. And it's exactly the same value that I was given here. Therefore, we know that we don't need to interpolate, that the temperature of this phase is 500 degrees C, and it has the internal energy that we were given. So I can go ahead and plot that on a TV diagram or TS diagram. It's the state exists where the 10 bar pressure line crosses the 500 degrees C line, and that is out here in the superheat vapor region. And all I have to do now is get the value of entropy at this state in the table, which is 7.7622 kilojoules per kilogram K. Now the third problem we're asked to solve is for refrigerant 134A, not for water. We have this refrigerant at a temperature of minus 22 degrees C. We're given that its quality is 60% and asked to find the value of entropy. Well, because its quality is given, we know that it's a saturated mixture. So we'll go to the R134A saturation table, and we'll find a row where the temperature is minus 22 degrees C. And we'll get the values of S sub F and S sub G for that temperature. Now, I can calculate the quality is just the quality of a mixture is just S sub F plus the quality times S sub G minus S sub F. So having gotten those two values out of the table, I calculate a specific entropy of 0.5969 kilojoules per kilogram K. And that's a simple plot on a TS or TV diagram. We have a constant temperature line of minus 22 C, and we're under the vapor dome at a quality of 0.60. The final part of this problem is for ammonia, which we are given at 28 degrees C, and we're given this specific entropy. It's 4.9948 kilojoules per kilogram K, and in this case, we want to find the internal energy. So we'll go to the ammonia saturation table at 28 degrees C, and we'll look at the value for entropy at the saturated vapor, and it's 4.9948, exactly the value we were given. So we know that this is a saturated vapor state, all right? And so that's going to plot on our TV or TS diagram on the 28 degree C temperature line, right on the saturated vapor line. And so we can now find the internal energy in the table. It's just U sub G, which is 1336.2 kilojoules per kilogram.